Done.
Okay. Hello. Hope everyone can hear me. I would encourage you, if there are any issues that you're having, to use the chat function to communicate with us. Also, during the talk, I'll also encourage you to use the chat function if you have questions. And so there will be time for kind of Q&A at the end, and I will read the questions and Dr. Dutton will respond. So my name is Marty Hilton. I'm the director of the University of Florida's Preservation Institute in Nantucket. And I was asked to, by the executive director of Maria Mitchell Association, Dave Gagnon, to stand in for him this evening. He had something come up. So, but Dr. Dutton, who's now at the University of Wisconsin, is a former colleague at the University of Florida, so it's happy to reconnect. First of all, I want to welcome all the attendees to the Maria Mitchell Association Science Speaker Series, and to thank all of the MMA members, as well as our sponsors, including the Osceola Foundation, the Acclimate Initiative, Nantucket Island Resorts, and Cisco Brewers for supporting the series. Again, just remind you, post any questions that you might have throughout the talk, and I will read those at the end. And with that, I'm going to introduce Dr. Dutton and turn it over to her. Just pulling up the bio here. Andrea Dutton is a world-renowned expert on past climate and sea level change. Her research focus is to establish the behavior of sea level and polar ice sheets during past warm periods to better inform us about future. She is very active in communicating her research to the public and has been extensively quoted and featured in popular media. Andrea's combined impact within academia and in the sphere of public outreach has earned her many accolades, including being named as a fellow of the Geological Society of America, as one of Rolling Stone's 25 People Shaping the Future, and most recently, and congratulations, a MacArthur Fellow. And with that, I'm going to turn it over to you, Andrea.
Terrific. Thank you. And thank you to everyone who has joined us here tonight. I know this issue is very real for many of you, but it's also maybe hard to make space right now in your life for something else that might sound like a depressing topic. But I am hoping not to be too depressing tonight and to give you some hope about reimagining the future, which is why I kind of chose the title that I did, to think positively about what we can do about this issue we're facing with sea level rise. And that hopefully some of the knowledge that I share with you, you will find empowering so that you can go forth and basically be active to address this issue in the future, instead of having a passive role of waiting for it to happen. So for those of you, I'm sure many of you spend a lot of time on video conference calls right now, but I just wanted to say that in Zoom, it usually defaults that there's a little video screen with my head in the upper right-hand corner. If there's something on the slide behind there you can't see, you can actually click on it and drag it away. I've tried to reformat my slides so there's nothing important up in that corner now that I'm doing a lot of Zoom presentations, but I just wanted to let you know how to do that in case that's a problem. Okay, so I wanted to play a brief 2-minute video for you to introduce myself, and it's unfortunately I tried to test it before and it's not going to work tonight. If you would like to watch this though, it's a 2-minute video, and if you Google my name and this title, Planning for Our Place Amid Rising Seas, or you could just Google YouTube Andrea Dutton and probably find it. This was made from my time at the University of Florida. They made this short promotional video that really, it is a nice introduction to my work, and it's really nice because it's a video and you get to see me in the field, what I do as a geologist. So I'll try to summarize what that 2-minute video shows you. I study past sea level change by looking at fossil coral reefs, because those corals grow close to the sea surface because they need sunlight to survive. And so we use them to track the position of sea level through time. And so I go out to field sites around the world looking at fossil coral reefs, sometimes ones from when sea level was higher, so they're now sitting above sea level, and so we can get access to them. They're usually near the coastlines. Sometimes we are drilling reefs that are now submerged below sea level. And we use those to reconstruct, what is the magnitude of change in sea level for past warm periods, and how quickly does that happen? Because we want to understand better how quickly that's going to happen in the future. And to some extent, in the past, the Earth has done that experiment for us. Because it has been warmer in the past, the Earth didn't increase temperature as quickly as we are doing today, but we can still use it as a partial analog for what we're looking at in the future. And so that gives you a little bit of an idea of what I do as a scientist. And I'm going to share with you today some of the results of that research, looking deep in time. Also talk a little bit about some work we've done looking at sea level changes more recent on human timescales using tide gauge data. And think about, with that knowledge, what implications does that have for us making policies as we move into the future, and how we can use that information to our advantage moving forward. So the island of Nantucket has a really interesting history, and it is one that is intimately linked with both ice sheets and sea level rise. So many of you probably already know this, but when these large ice sheets advanced across the North American continent during the last ice age, about 20,000 years ago, the edge of the ice sheet sat right about where Nantucket is now. And so you can think of the ice sheet basically as like a snow plow pushing everything in front of it. So all the dirt and the rocks and the sediment and so forth. And so you end up with these ridges that are moraines. And that's what's shown on the right image over here in red, these kind of high points that were pushed up at the edge of the ice sheet there. So that's why these islands actually are here and sit here. It's because of this ice sheet advance. And then as this ice sheet retreated northwards, as it started to melt back, the ocean, the sea level rose across this continental shelf, which was exposed during the last ice age, and then it became covered as sea level rose up. And at some point, eventually, these islands here of Martha's Vineyard and Nantucket became separate from the mainland as sea level rose, I think right around 5,000 or 6,000 years ago. So the reason this island is here is because of these changes in the size of the ice sheets and sea level change. And it's a dynamic Earth, and it's going to continue to evolve. And so even though on human timescales, we may think of this island or this landscape as somewhat static, it is very dynamic, and it's going to continue to evolve in the future. And I think coming to terms with that is one of the harder things that we have to do. We can come in as scientists and say, well, this is what's going to happen. But I think the harder part is working through all the emotional response that comes with that idea that, the Nantucket of the future is not going to be the same as the Nantucket of the past. And that's a hard thing to get past, no matter what coastal community you are from, for sure. So I wanted to frame kind of an overarching view of what I'm going to say today with the whole bad news, good news. And so the bad news is that there's a certain amount of sea level rise that is already baked into the system based on the amount of warming that has already happened. And I'll talk about how much that might be in a little bit. But we can make the ultimate amount of sea level rise less bad than it needs to be if we take action. So any action that we take to reduce our carbon emissions can change the ultimate outcome of how much the sea level rises, and even how fast that might occur in the future. So that's the good news. In addition to that, this concept that I just spoke about on the last slide, this idea that the future is going to be different. And a lot of people see that as bad news, even though it's inevitable. But the good news is we have actually quite a good handle on what is happening and why it's happening. We know that sea level is rising. More than that, we know that it's accelerating. So we can use that information to prepare for how we want this to play out. So instead of spending all of our emotional energy fighting the part that we can't control, the part that's baked into the system, we can use that more positively to say, instead of just waiting for this to happen passively, we can put our knowledge to use and make a decision on how we want this to play out as we move into the future. Because as I often like to say, the future is not just a place that we get to go to, it's a place that we get to create together and as a community. So this is the big thing that I want to project to you tonight, is to try to learn how to embrace the future rather than being overcome by fear and fighting it, which of course right now with everything going on in the world is all too easy to do sometimes. And so I've fallen back on this kind of common quote that you hear a lot of times, which I think is a real guiding principle also when we come to climate change and thinking about climate change, is that we should think about it in terms of having the strength to accept the things that we can't change, so the part that's already baked into the system, but to have the courage to change the things that we can, and not just hope, kind of a passive hope that it will get better, but active courage for all of us to get involved in this, and the wisdom to know the difference. And so I'm hoping that by participating in this tonight, I can help you a little bit with all three of these things that are underlined here: the acceptance part of the story, the courage part, and also the wisdom by sharing some of my knowledge about the science of sea level rise with you. Okay, so as we think about that future, what is it going to look like? And I used to give talks about sea level, and I only talked about sea level rise without really talking about the context of climate change. And it turns out a lot of people came away from those talks not really understanding the connection. So I want to start with climate change first, and then move to sea level rise. So these global warming stripes, many of you may have seen before, are familiar with. It shows temperature change on a color scale going from 1850 on the left side of the screen over to 2019 on the right side. And this is the global average temperature change over that time period. And when you look at it this way, it is really striking visually to see this acceleration in the rate of temperature change moving into the future. And when we think about our lifetimes, and you can pick the stripe on here for the year that you were born, it's very clear that what the future is going to be, and the future for our children and our grandchildren, is really not going to resemble the world that we knew in many different ways. So some of you may know some of this part about climate change I'm going to talk about now. Some of you may not be familiar, but for all of us, I think it's good to refresh our memories on some of it, especially when we go out and have conversations with other people, because I think that's one of the most important things that all of us can do when we approach this problem, is to talk to other people about it. Sometimes people are afraid of bringing up this topic with other people, but the more we talk about it, the more we will be able to adapt and to make progress on it as we move into the future. So the first question is, how much of global warming is due to humans? And this is something that people still ask all the time, even though this is something that scientists have been sending very clear messages on for a long time. I've made that message very clear with the parentheses right underneath the title on this slide, and the hint that the answer is all of it. There were a couple op-eds that came out a year or two ago that framed this question in a really neat manner. It's something that I talk about. This is my research. I feel like I'm kind of a detective of planet Earth, and I look at all of these clues in the rock. I even look at chemistry, even some of the isotope chemistry, some of the same things that forensic scientists use on crime scenes. We use some of the same tools actually when we're looking at rocks in the past to figure out what happened in the past, how much of the temperature change, and how much of this is due to humans. And it turns out that when we look at the evidence, we find the fingerprints of carbon dioxide everywhere. Carbon dioxide is like the world's dumbest criminal because it leaves evidence all over the place that it's guilty. And there's lots of different lines of evidence that we have in the rock record that we can use to look at this. But in addition, we also have models that we can use. And when we run those models back in time to try to reconstruct the changes in temperature, so this graph is showing you from the late 1800s over to the year 2010 on the right. If the only thing we put into that model are natural factors, like how much of sun's energy is coming into the earth, or how does volcanic emissions change the temperature of the planet? If we only consider the natural factors, what the models give us as the output is shown in blue here. And it does not reproduce this steep trend, this rise in temperatures that you saw in that color chart that I showed you before. The only way we can get the models to reproduce this trend in temperature is when we add in all of the human factors as well. So once we add in greenhouse gases, aerosols, which are the tiny particles like from pollution that get into the atmosphere, land use changes that affect temperature, We put all these things in together, then we can reproduce that trend. Because without it, actually, the climate would actually be slightly cooling. So it's really the greenhouse gases is the biggest factor here in getting this trend to happen. So we have direct evidence from data that we've collected looking at the geologic record from the past. We have model evidence, and all of it shows us that all of this warming that you see here in this graph, the difference from the blue to the pink, all of it is due to humans, right? So that part is very clear. Second part of the story, I often get asked as a geologist, well, isn't this just part of the natural cycle, right? This is something that you hear politicians fall back on a lot because they know there are natural cycles. And so then it tends to confuse people. Well, okay, maybe that's true. But I am here to tell you as a geologist that we have definitely thought about this. We've been researching it for decades and decades, and this is not part of a natural cycle. Some of my colleagues go out and do this field work. I just spent 6 months in New Zealand with a bunch of people who go to Antarctica all the time. And one of the things they do is collect ice cores. And in that ice, there are these tiny little air bubbles that you can see in this picture here. And those air bubbles have trapped atmosphere from the past. So we can directly measure the composition of Earth's atmosphere back through time and know exactly how much carbon dioxide was there. We can tell you what temperature it was. It's really amazing the things that we can recover from these past records. And when we look at those records, this graph shows you 800,000 years ago on the left. Time is moving to the right here over to present day on the far right side. These are the natural cycles in the record of carbon dioxide concentration in the atmosphere, which varies in concert with temperature, which varies in concert with concentrations in methane through time. And when we look at the values for the present day, we are literally off the charts. Right? There's no question. This is not part of the natural cycle. We have broken free. We are way outside of this envelope of variation. So this is very clearly not just part of a natural cycle. So when we turn to thinking about sea level rise, how does this compare against the context of what has happened in the past? So this graph shows you sea level change in millimeters over here on the vertical axis, and it goes only from 1993 to present. That's because that's when we first sent up the satellites that collect this altimetry data looking at global sea level rise across the globe. So we only have this satellite record for a couple decades. Going farther back in time, we use tide gauges for the historical record. And if you average the rate of change over this time window that you're looking at here on your screen, it's about 3 millimeters a year. Right? And that's about the thickness of 2 pennies stacked together, which does not sound like a lot. And so if you own coastal property, or, you know, some people, I used to live in Florida and I would show this number to people and they'd laugh at me and say, why do I need to worry about 3 millimeters a year? It's because we have built right up to the edge of the coastlines with all of this hard infrastructure. And in the past century, sea level has already risen on average about 8 inches or more now, actually. And so we're already at this tipping point. We've built right to the edge and things are already flooding into the streets, as I'm sure many of you have seen in different areas along our coastal seaboard in the United States and elsewhere. And so while this doesn't sound very fast, it has made already a very large change to our landscape that you can see. So here in this image, this is an image of Long Beach Island, New Jersey. And there are barrier islands like this that stretch all up and down the east coast of the US and in the Gulf Coast, and they're made of sand. And sand, as many of you know, we've all played in sand pits at some point in our life, sand moves. And as sea level rises, these barrier islands want to retreat as sea level rises and they retreat landward back. And you can see this area here towards the north where they've built on it and everyone wants it to stay where it is, right? And this area that's been left natural and has not been developed is retreating as sea level is rising. And so it's no surprise that this coastline is really now out of equilibrium with the position of sea level. And so when we get big storms that come along, it's no surprise that Long Beach Island looks something like this. And so this is an image from after Hurricane Sandy. And this island really should not be in this position anymore, and it's not being allowed to move. And so it's becoming more and more vulnerable the longer that we keep it in that fixed position and that we defend that coastline right where it is today. So if we go back to this graph again, how does this 3 millimeters a year compare? We've already seen the amount of change on that island that it's already having. Compared to the last century, the rate was only about 1 to 2 millimeters a year. And that's actually a very large increase, 3 compared to say 1. And it is continuing to accelerate. Even over this small time window I'm showing on this screen, which is only a few decades, there is a statistically significant acceleration signal in there. It's now closer to 4 millimeters a year right now. So this acceleration is largely due to the increasing contribution of meltwater from the polar ice sheets, where climate change is proceeding very rapidly near the poles and causing ice to melt in the polar regions. So I'm talking about ice from on Antarctica and ice in Greenland. So looking over this past century here, so this is 1900 on the left, it's about 2010 here, or 2020 on the right, I guess. And again, this is sea level in millimeters on the vertical axis. These are 3 different reconstructions that people have done from the tide gauge data. They start to diverge as you go back in time because there are not very many tide gauges, and so it becomes hard to interpolate what was happening with the global average. But no matter which one of those you look at, you can really see that sea level was rising and it was accelerating in all of those different reconstructions as well. So in that time period, sea level rise was dominated by 2 things. The thermal expansion of water as it heats up and expands causes sea level to rise, and also the melting of mountain glaciers. But in this century, we expect the dominant cause of sea level rise to be this acceleration from the melting of the polar ice sheets. So this mass loss from the polar regions is expected to far exceed these other contributions to global sea level rise under future warming. And so the question is, how is that going to play out? Because we have never lived through a time when it was warmer than it is today, where we could see, well, how do these ice sheets respond to this warming? How far are they going to retreat? How quickly is that going to happen? So that's where we as geologists can step in and say, well, the Earth, again, has to some extent done this experiment for us. We can look at past warm periods to see when it got warmer than present. What was the answer to these questions? How sensitive are these ice sheets to warming? Do we need to worry about this at all? And how quickly did that happen? And so that's really the main focus of my research as I look into the deep past. So again, as I explained to you earlier, I use fossil corals to reconstruct the past position of sea level through time. This takes me all over the world to tropical islands, which is not a bad deal, I have to say. I chose well for my career. And you can see pictures of me here in Western Australia, which is one of the sites that we have been to many times, sampling some of those corals. We do really detailed surveying. It's more complex than this picture. We don't just lean a yardstick up against the outcrop. But here's a case where you have this exposed fossil reef sitting above sea level now, and it's a tectonically stable coastline. So this is recording a time period known as the last interglacial. It's a warm period. The last warm period before the last ice age, about 125,000 years ago. And I'm going to talk to you a little bit about that time period today and what we've learned by studying it. So I'm a part of an international group of people who study ice sheets and sea level back in time, trying to gain some empirical evidence on what's going to happen in the future by looking into the past. And several years ago now, we put together a paper that summarized our state of knowledge. What do we understand from these past warm periods that can tell us from the future? So we had ice sheet modelers and climate modelers and people like me who reconstruct sea level. All people who are looking at it from all different angles come together to do this analysis. And so I'm going to share with you kind of the cartoon summary of the paper. So it's not the simplest cartoon, so I'm going to walk you through this step by step so you can see what's happening here. So in this paper, excuse me, we looked at warm periods over the last 3 million years. Okay. And we chose the warmest time periods in the last 3 million years. There's this one here, 125,000 years ago that I just mentioned to you, called the last interglacial. And then these 2 other ones, about 400,000 years ago and about 3 million years ago in the Pliocene. So at the top, it shows you what the global average temperature was for each of those different time slices. So even today, we have warmed up the Earth a little bit more than 1 degree Celsius relative to pre-industrial conditions. And we have done that by emitting all these greenhouse gases into the atmosphere very quickly. And this shows you that sea level is at 0 today, kind of by definition. We're going to call that 0. And this is the present configuration of the polar ice sheets. And as you look to the right, you can see how this changes for these past warm periods. And so we found that no matter which of these time intervals we looked at, that sea level consistently rose at least 6 meters or more on average around the globe during these time periods when the global temperature was anywhere from 1 to 3 degrees warmer than today. So what this is really telling us is that we've warmed up temperatures so quickly that these ice sheets are now out of equilibrium with the temperature. Because in the past, when we raise the temperature by that much and give the system time to respond, sea level has risen quite a lot, right? So people used to think these ice sheets were so big that they weren't that sensitive to what might sound like, very small amounts of warming. This tells us that, in fact, they are quite sensitive to that. So, here we go. So that was the main takeaway from this paper. During these recent warm periods, they're known as interglacials because they're between the glacial periods, these warm periods. Small increases in global mean temperature of just a few degrees relative to the pre-industrial results in at least 6 meters, that's about 20 feet of sea level rise. GMSL, I should say, is global mean sea level, average sea level. So over the past decade, I spent most of my time living in the state of Florida. And this is what Florida would look like with 6 meters of sea level rise. And this actually makes sense because most of South Florida, if you go down there and look at the rocks, they are limestones and shallow marine rocks from this last time period, from the last interglacial. So we know that the seas were there and did cover that part of Florida during that time when the global average temperature was about what it already is today. This is what New York would look like with 6 meters of sea level rise. And this morning I went to this site here at Climate Central where they put together this nice visualization of this result from the paper for us to see what it would look like closer to home for you in Nantucket and Martha's Vineyard. So this may be one of the most depressing slides of the talk. Sometimes I do get called depressing Dr. Dutton, and I have to say I don't shy away from laying out the truth here, is that we may have already committed ourselves ultimately to sea level rising this much, even from the amount of warming that has already happened. And that is what the geological record is telling us here. But I need to balance that with some good news for you. Good news is this is not going to happen overnight, right? We're not going to have 6 meters of sea level rise tomorrow. We're not even going to have 6 meters by the end of the century for sure. But the real question is, how quickly is this going to unfold? And that is the burning question right now in my field of study. We're trying to get a better handle on the mechanics, physical mechanics of this ice sheet retreat. How quickly did sea level rise when this happened? And I focus on dating these corals and trying to provide a chronology, so a time scale that this happened. And that is the main focus of my research group right now, trying to answer that question better. Because right now, it is very poorly constrained in terms of how long that might take to play out. So when we look at this time period, this last interglacial period, 125,000 years ago, our best estimate is that sea level peaked around 6 to 9 meters above present, so it's about 20 to 30 feet. So the question is, where did that come from if we want to understand which ice sheets are vulnerable to this change? So we kind of put together this budget. Some of it you can attribute to some thermal expansion of the water. You can melt all the mountain glaciers we have left on Earth, and those two things only give you about 1 meter at the most of sea level rise. We know that part of the Greenland ice sheet did melt during this warm period. We know that evidence from ice cores and from models and from marine cores around the Greenland continent that tell us that part of the Greenland ice sheet melted, but not all of it. So that may have raised sea level by, on average, about 2 meters around the world. So to get anything more than about 3 meters, you really need to tap into the Antarctic ice sheet. And so that was one of the big takeaways from the work that we've been doing on this time period, is that it implies that a sector of the Antarctic ice sheet may have collapsed during this past warm period. And when you read about sea level rise and projections for the future in the news, you probably hear a lot about Antarctica. There was some news today, there's a new paper out in Nature that talks about exactly this issue, this vulnerability of the Antarctic ice sheet during these past warm periods and what happened. So the reason that parts of the Antarctic ice sheet are very vulnerable to this warming, and people talk about there being kind of a tipping point for this process to take off, is that as the waters in the Southern Ocean warm around the Antarctic continent, they're kind of, you think about them as bathing the underbelly of the ice sheet. And that's kind of shown in this cartoon image here, that these warm waters underneath are melting back what we call the grounding line. And that's the point where the ground and the ice and the water meet right here. And right now, the ice sheet is kind of pinned on this high point here when you look at it. Because of the weight and the thickness of this ice sheet, it's pressing down on the Earth's surface. You can see that the land surface is going down as it goes back because of the weight of the ice sheet. Once it gets past this high point, there's nothing to stop it from sliding back and sliding back and sliding all the way back. So this is thought of as a tipping point, that once you cross it, you can't really stop that process until it reaches its new equilibrium position. So even if we stopped emitting all carbon today, I'll trade it in our SUVs for skateboards, you know, as if you could just turn that off instantly. If we've passed this tipping point, you wouldn't be able to stop that, right? So some of my colleagues who study modern measurements from the ice sheets argue that the collapse of the West Antarctic ice sheet has already begun and that we've passed this point of no return. This is a picture that was taken of the Thwaites Glacier, which is thought to be one of the most vulnerable parts of the West Antarctic ice sheet. Has this geometry, like I showed you in the past diagram, where the base of the ice sheet is below sea level, and it's very susceptible to this rapid retreat. This was from a research cruise that went there about a year or so ago. It's the first time people had ever been to the edge of the Thwaites Glacier before. Obviously, the penguins have been there a lot. People had never been there before, and they're studying this part to understand how it's responding to the warming right now, and to see whether we've kind of passed this tipping point yet or not. The problem with this whole conversation of tipping points in my mind is that you don't really know where the tipping point is, like, until you're past it. And you say, oh yeah, there it was, right? And now sea level rates, you know, the sea level rise is increasing much faster. We know we're on this trajectory, but we're not going to know that for decades, even if we've already passed that tipping point. At some point, things might change from millimeters a year to centimeters a year, right? 10 centimeters a year. And that's when things will really kick off. And we obviously want to prevent that from happening if it hasn't happened yet, right? So what does all this knowledge about the deep past imply as we try to make policy around sea level rise moving into the future? One is that our actions today kind of create this commitment, this sea level commitment of what's going to happen in the future. This rise in sea level is going to play out over a long time scale. So the sea level rise that we are witnessing today on our coastlines is really just the first step in what is going to be a very long journey of coastal retreat as these ice sheets re-equilibrate to this rapid change in temperature. I like to think of it as throwing 2 ice cubes into a warm room and watching what happens as they melt. And that's basically what we've done with these ice sheets. We've thrown them into the warm room and we're standing back and watching in real time how they're responding to this change in temperature. But one of the outstanding questions here is, how does this sea level rise play out? Is it gradual? You know, does it gradually go up, or is there going to be a rapid collapse of an ice sheet where we have this big, huge step of like a meter or something as sea level goes up? Or is it going to be more like going up a staircase as little outlet glaciers collapse? And to me, answering that question is something that we can do by looking at the past records. And it's very important for coastal planning, right? Because planning for a rapid jump at some point, and we're not quite sure when, is a very different ballgame from planning from something that's just going to be gradual. And I'll come back to that concept a little bit later. So this idea of, you know, this sea level commitment makes you realize that, you know, as we are making choices about who we're going to elect to office and the politicians who are going to be making some of these policies for us, they are making decisions for the next 100,000 years of what's going to happen, right, at some level. And so that's how we need to approach these decisions that we're making in our lives today. The actions we take are going to have consequences for a very long time. So the more that we can change our actions now, the better that outcome ultimately will be. So now I'm going to shift gears a little bit and talk about a different timescale that might be a little bit more relevant to you, as more human timescales of sea level rise. with some of my colleagues at the University of Florida. We started looking at tide gauge records because of one of the projects that one of them was doing out on the east coast of Florida. He was trying to understand his data, brought this tide gauge data to us and said, this isn't right, is it? Can you help explain this to me? And so we started to put our heads together, and it resulted in this paper that got featured here in the New York Times because it was a really important advance in our understanding of the dynamics of sea level on these timescales and what was controlling it along the east coast of the US. And so what we were looking at is shown here in this graph from about 1996 to 2015. And these are 3 tide gauges all on the east coast of Florida, showing sea level rise, and kind of smooth the record a little bit so you don't have to see all the noisy data, just to get a sense of how it was rising over that period of time. And you can see that during this window of 2011 to 2015, there was this rapid uptick, acceleration in the rate of sea level rise. And we first saw this in one tide gauge, and we thought, maybe there's a problem in this tide gauge because, this is a huge, order of magnitude increase in the rate of sea level rise. So we started pulling up more data, and sure enough, as you can see here, all up and down the east coast of Florida, the more we looked at it, it turns out everywhere from like Key West all the way to Cape Hatteras in North Carolina showed the same response, this very rapid acceleration in sea level rise that played out over 5 years. And then it waned a bit, kind of came down to this long-term trend that you see in this picture. Not unlike some things that have happened in the Northeast, closer to Nantucket. Sometimes there are these, they call them hotspots of sea level rise, where you get this rapid accelerations of sea level rise over a few years, and then it kind of dies down a little bit. But the big thing to read here is what's at the top of the slide. It says, we saw 5 inches of sea level rise in just 5 years, right? So you remember that 3 millimeters a year number I started out with near the beginning of the talk? If you take 3 millimeters and average it out over a century, that would give you only 12 inches of sea level rise, right? That's what 3 millimeters translates to. We're looking at 5 inches in 5 years. No one is planning for that rate of sea level rise in any community, right? Yet it turns out that this is a natural part of the system. We looked at tide gauge records going back over the whole last century, all up and down the east coast of the US, and we found that these short-term accelerations can occur anywhere along the US Atlantic coast, and it was driven by the interaction of 2 large climate oscillations, the El Nino signal and something called the North Atlantic oscillation, which is basically a pressure gradient over the North Atlantic basin. You can think of it like a seesaw of the atmospheric pressure pushing down on the ocean and how that kind of rocks back and forth naturally. And the way that those 2 superimpose can basically cause water to pile up along one part of the coastline for several years before it kind of can go back out into its normal circulation pattern. So that can happen here in the southeast. That can also happen in the northeast, up where you are as well. And so this is something that needs to be taken into account when we are making plans in coastal regions. So some of the lessons in terms of looking at this recent sea level rise is that hotspots are a threat to this entire eastern seaboard. They can produce high rates of sea level rise, like 1 inch per year. And we need to account for the possibility that these will happen. They happen naturally, superimposed upon this longer term trend of global warming driven sea level rise that's causing sea level to rise over the long timescales. But there's still a lot that we don't understand about these natural variations. And so there's ongoing research trying to understand, can we predict when they're going to occur? That'd be very nice to be able to do. And also how long that they would persist, right? Because having it there for 1 year might be very different than having it over 5 years. 1 inch is a lot different than 5 inches. So that's an area of active research that's happening now. So when we as sea level scientists go into communities and talk about sea level rise, this is really one of the main tools that gets used to communicate about what's going to happen in the future. Some type of sea level projection chart, like I'm showing you here. This one comes from the National Climate Assessment. It was published a couple of years ago. And these are feet in numbers that are here on the vertical axis to the left. This purple part is the satellite record I showed you before. And then these are different projections for the future, where this red curve is kind of a worst case scenario where we pass that tipping point and start to kick off that process in the Antarctic ice sheet, versus this darker blue curve at the bottom, which is just a linear, straight extrapolation of the satellite record, which is actually incorrect. And I feel like it shouldn't be on this diagram because we know that sea level is accelerating. It's going to continue to accelerate. And so it's not going to be that linear one. It's going to be somewhere above it. And those just show you an array of different scenarios that might happen. And a lot of people look at this and say, well, you guys have no idea what's going to happen. There's so much uncertainty in this picture that we don't know what to do. So we're not going to do anything because you can't tell me when, where sea level is going to be in the year 2050. You look at this and we have no idea. But I like to flip that on its head to say, well, actually, there's an incredible amount of certainty in this picture. We know that sea level is rising. We also know that it's accelerating. And so we have a lot of certainty about what's coming in the future. We may not be able to tell you exactly what that magnitude is going to be on a certain day. I also can't tell you what day the next hurricane is going to hit Miami, but I can also tell you that there will be a hurricane that hits Miami in the future, right? So we need to plan for that. And there's no reason to delay action based on any uncertainty that remains in terms of how quickly this process is going to play out, because it will play out eventually. So the more that you plan now and the higher curve that you choose, the better position you'll be in as you move forward in time. Having said that, I can also tell you this. These are very useful projections, but I can guarantee you that sea level rise is not going to look like any one of these curves. This is a very unusual language for scientists to use to say they guarantee something, but that's because I know what the data looks like. And I'm going to show you here what that data looks like. So this is, oops, sorry, I pressed the wrong button. Tide gauge data that you're looking at here from Virginia Key, which is near Miami, Florida. And this is, again, this axis is in feet, so 3 feet, 4 feet. And going from the year 1996 over to, oh, sorry, I thought I put the one up to 2020 in, but this one only goes through 2018. But you can still see the major points here. So tides go up and down every day. This is a very noisy signal. The other thing you can see here is this annual pattern of high tides in the fall, which happens naturally here along this coastline, lower sea level in the spring. So there's this annual signal that you can see in the data. And then when you look back in time, you can see these storm surges from hurricanes. So here's Hurricane Irene, Hurricane Rita, Hurricane Wilma, right? This is active time for hurricanes in Florida here. Hurricane Sandy did not make landfall in Florida, but still created a storm surge that was big enough that you can see it in the signal. And then here you get king tide, king tide, king tide. Had I shown you the one from 2020, you would have seen more king tides at the same level as what we used to get only during hurricane storm surge. So while sea level has been rising gradually in the background, now we're getting this extreme coastal flooding more often, and these king tides are much worse than they used to be. And this is how sea level rise is going to play out. It will be dictated by these extreme events that are going to happen more and more frequently as we move into the future. You could see Hurricane Irma here, which I didn't point out. A lot of these hurricanes come in here, as if you look at the dates, around September or October, which is right on top of the king tides, which doesn't help. And so this one was a big one, this storm surge that came in with Hurricane Irma. So the point here is that, I've talked to architects in this area who are working and say, well, if you could just tell me where sea level is going to be in 2050, I can build to that. That's fine. So, is it going to be 2 feet in 2050? Fine, I can plan for that. But the point is, it's going to hit 2 feet before 2050. If you look here, we're already pushing 2 feet above kind of normal, or what the background signal, in some of these extreme events. And that's just going to become more frequent until it's on average at 2 feet. And that doesn't really come across when you look at that graph from the last diagram, those sea level projections that make it look like, oh, it's just going to happen gradually. We're not going to get to 2 feet until 2050, maybe, on one of those curves. But in fact, that's not the story at all. And so a better way to frame this is to think about the frequency of coastal flooding, which a lot of people are already doing. About how often is it going to reach that point as we move years into the future? Because maybe you can tolerate being flooded 1 day a year, 2 day a year, but maybe not 2 weeks a year, right? So this diagram here on the left is showing the percent increase in the frequency of coastal flooding at sites around the US using data from 2017 compared to 2000. So over a 17-year period, they saw more than a 200% increase in some of these sites in the dark red. Frequency of coastal flooding in the US from high tides alone has doubled in the US in just 30 years. Right, so this is really how sea level rise is going to play out. It's about frequency of flooding. It's about how many consecutive days of flooding you have back to back that will impact people. So when you think about it in this sense, sea level rise is actually going to happen sooner than most people think it will, just by looking at those sea level projection curves I showed you before. So in my mind, those projection curves are really almost doing us a little bit of a disservice because they are very misleading, because it's not telling the true story that we're going to reach those levels before that graph gets there, because that's just when it's going to be there on average. Okay, so cognizant of time, and I need to wrap up. I had a lot more I wanted to say, but I'm going to move through this last part a little bit quickly and then have time to take questions. There are a lot of impacts of sea level rise as we plan. It's not just about inundation, even though that's usually what people think about when they think about sea level rise. It's not just about still building a seawall, because a seawall won't stop salt water from intruding underground into freshwater aquifers, for example. So when we think about sea level rise, we really have to think about this whole suite of issues and all these different impacts as we make adaptations and try to address this into the future. I want to share a brief story about a study that came out last December in the Keys, because it's very interesting. They were looking at a single stretch of a 3-mile stretch of road at the southern tip of a key called Sugarloaf Key, which is just up the highway from Key West. And using sea level projections for that region, the best that they had, they projected that by 2025, they would need to raise that road by 1.3 feet so that it would stay dry. And that would cost $75 million. And you can see how those numbers blow out as you move into the future. $181 million to keep it dry in the year 2060. Mind you, even still, if you keep that 3-mile stretch of road dry, that water that you've displaced has to go somewhere, and it's going to go into people's yards who live next to the roads. It's actually going to make the flooding worse locally when you raise the roads in front of your houses, right? The reason this is remarkable is because it was one of the first times that public officials have said this, that we can't save everyone. You know, we just can't engineer our way out of this, which has been the approach in a lot of places. And that doesn't mean there's not a time and a place for some engineering to buy us some time, but it is not going to be the end-all solution. And so they were forced to admit here when they looked at the numbers that as the seas rise and the flooding gets worse, not everyone can be saved. I want to have a brief word about seawalls too. I can't leave without saying this, because seawalls are erected in communities that can afford them. And again, that displaces the water that would have gone there into the communities that can't build the seawalls. It makes it even worse for those communities. So a recent analysis of federal flood insurance data that included inland as well as coastal flooding showed that this flooding disproportionately harms African-American neighborhoods, because a lot of those poorer neighborhoods have ended up on lower ground in places that get flooded more often. So there's a huge social inequity and social justice issue that we need to think about with a lot of these engineering things that get proposed. Secondly, the thing about seawalls is I feel like they build in a false sense of complacency for the communities behind those seawalls. So if we just look at New Orleans, Hurricane Katrina, if you're building a wall, you're basically living in a bowl. And at some point that wall will get breached or it will fail. And at that point, you are completely unprepared because you thought you were safe behind the wall. So then it's even more catastrophic and more damaging because you were not ready for it because you thought the wall would work, right? So sea level walls are often a first gut reaction of community, let's build a seawall, but you really need to think through this process that it's not going to be the end-all solution. When you think about creating a resilient community in Nantucket or anywhere, I think it's important to remember it has to be a community initiative. This picture many of you may recognize from Mexico Beach on the Florida Panhandle when Hurricane Michael ripped through there. This house was left standing because it was built way above code, right? And it was built to withstand these floods and so forth. And a lot of people held this up as a picture of resilience. Hey, look, this is resilient, this is great. But this guy, okay, he's got his house, but he's got no neighbors, he has no electricity, he has no water, his community is gone, right? And so is probably the value of his property largely. So this is not the definition of resiliency. So resiliency cannot be achieved at an individual level is the big point here. It really needs to be a community-wide issue. So I would implore you that instead of waiting for the politicians to stand around as the sea level rises above their ears, which actually has literally happened this last year in Italy, as this Italian council had to evacuate the building In Venice, after this horrible flooding that happened, right after they rejected some measures on climate change, right? So here they are literally debating it while the water is rising up around their ears. That you get out there and take some action to reduce our emissions on climate change, any way that is. Maybe you're a banker and you do something in terms of finances. Maybe you're an artist. We all have talents that we can bring to bear on this issue. And there's not just one way to address it. So these are images of our life right now. Climate change is not just something that's going to happen in the future. It's already impacting our lives right now, today. Nantucket could be an example moving into the future of how to adapt to this change. Nantucket has been through a lot before. This graph shows whale oil use back in the 19th century, along with the price of that whale oil. This is the time when the first modern oil well was drilled. So there have been large energy source transitions in our history. And there were a lot of good things that we got out of burning fossil fuels. But now we've reached another point in history where we need to make another tough transition, but one that ultimately will lead us to a better life. So as we go through this global pandemic, I hope that this experience has given us really some global continuity of experience in learning that the actions that we take really can have a change on the outcome of the problem that we're facing. And we can see that in terms of the actions we're taking with COVID-19 and how that's playing out in trying to flatten the curve. And while it might be hard to make space in our minds and our hearts to think about climate change on top of that, I would leave you with a word of warning that if we don't act soon, act rapidly, and make really big changes in what we're doing, that we will have even larger problems to grapple with as we move in the future. So again, thanks so much for your time, and hopefully you have some time for some questions now.
Well, thank you, Andrea, for, as always, a really enlightening and very excellent talk. I do have one question from Joel Bauman. He said, what is your opinion of geoengineering ideas to cool the planet?
Yeah, so that geoengineering is a real tough one. So what he's talking about here, one of the most common ones, there are different ways to do this, but thinking about ways to reduce global warming by essentially removing carbon dioxide from the atmosphere, or maybe shielding the sun's energy, right? So putting aerosols into the atmosphere that reflect some of that sun's energy that would then protect us from some of that warming. Ramping these up to scale is one of the big issues, right? Another big issue is not knowing exactly what's going to happen. So there may be some, anticipated impacts that we think will be good from the geoengineering projects that are proposed. But as is true with almost every example that we can look at where humans go in and try to manipulate ecosystems, for example, in the natural world, there are also some unanticipated impacts. And when you're doing something at a global scale like this and playing with global climate, those impacts could be huge and have a lot of impacts. Some of them we may have thought about, may have modeled and tried to understand, but they're going to be surprises in that too. And so geoengineering in many ways is very scary to me, but at the same time, we are also going to need some form of drawing carbon out of the atmosphere, literally, if we're going to reach some of these targets that have been put forth, like reaching only 1.5 or 2 degrees Celsius as we move into the future. And it may be that we need a suite of different types of projects at smaller scale. Being able to scale them up as quickly as we need to is probably one of the biggest challenges that we face in doing that.
Thank you, Andrea. Another couple of questions here from Vladimir Shrelinsky. Do you know, he said a couple of naive questions, but no bad questions.
No question is naive. They're all welcome.
Yeah. Do you know how much fossil fuel is left on Earth, and for how many years will it end up anyway before its burning has created real calamity? So how much is left on Earth, I guess, is the real question. Yeah,
there's a great book called The End of Oil. I think I read it when I was a graduate student, and it talks about, I highly recommend it. You can read about this issue. So geologists have estimated, how much oil reservoirs, how big they are, how many of them they are. So, and we haven't tapped them out yet. We haven't reached that peak level. So there's still a lot of damage that we can do. And so the message is we need to keep it in the ground, right? And the more that we keep it in the ground and the faster we do that, the better the outcomes are. So it's not just an issue of keeping it in the ground in 2050. The more that we keep in the ground now will also make a difference, because one of the big issues is how rapidly we are changing the climate, right? So the more we can do to speed down that rate of change, the better.
Well, as the grandson of an underground coal miner from southeastern Kentucky, I've witnessed firsthand the destruction, the extraction of fossil fuel can wreak. The other question from Vladimir was, is planting a lot of trees a solution to the growth of CO2 in the atmosphere?
Planting trees can be part of the solution, but is nowhere near the scale of what we need to draw down carbon dioxide levels in the atmosphere based on what we've put in. So planting trees is a great thing. It's a good thing. I highly encourage you to get out there and do it, but it's not the solution. And in fact, there is no one thing that is the solution. So it's not like there's a silver bullet. And it's not as easy. It's not one of these issues where, you know, a lot of us are used to going to things and we say, oh, there's this problem, and I write a check and we'll solve it, right? So you can't just like write a check on this problem and like be done with it. It's not one silver bullet. It's going to be, like some people say, like lots of buckshot, right? It's going to take a whole suite of solutions, many people using many different things for us to collectively solve the problem. So again, this is an issue where we need to come together as a global community. And it means not just the big countries and the big emitters, but also the small countries and the small states. You know, even Rhode Island, all the small states, everyone has a part to play. Because as the analogy I like to use is, if you're going on a journey and you want to get to your endpoint, well, you're not going to get there if you don't take the first step, or any step along that pathway, right? You need to take all the steps to get to that endpoint. So we all need to come together to reach those goals.
Really easy question. What was the source of the maps that showed the water projections for Miami, Manhattan, Martha's Vineyard, and Nantucket?
Yeah, those came from a website called Climate Central, and I highly encourage you to go check out their website. They have a project called Surging Seas, and they have a lot of wonderful visualizations and tools that you can use to look at. You know, you could basically have a little bar where you can raise the amount sea level and draw it down again, and a lot of statistics. So how many miles of roads get covered at those different points, how many schools, how many hospitals, how many airports, how many households, all kinds of different things. So it's a wonderful resource of information that Ben Strauss really led that project at Climate Central. So I highly encourage you to go look at that.
If I could also, if you search University of Florida Resilient Nantucket, we've been using the 3D laser scanning to model in 3 dimensions.
Great.
Level rise projections on the island. Maybe one last one here from Paula Korn. Please address Anthropocene, the epoch we've just entered, and what mankind is doing to this planet.
Right. So the Anthropocene is this term that people use to talk about kind of the current geological era, because basically, if you've seen from this talk, is that humans have become geologic agents, right? We're now creating changes that used to only occur on geologic timescales. And so that's where this word really comes from. And what it speaks to, though, is the impact that humans are having on this planet. And oftentimes when people talk about climate change, or they talk about saving the Earth, right? I don't usually talk about it in that respect. So I'm a geologist. Planet Earth has been here for 4.5 billion years, right? And it's going to continue to be here. But the question is, you know, how are we going to exist in this very rapidly changing landscape? So the reason that these changes are so dramatic and that we're so worried about them is because of how they're going to impact us. When you see pictures about sea level rise, you often see them associated with things like ice sheets and penguins and polar bears, right? But you need to think about how it impacts humans and put humans in that picture. I have an image I didn't show here tonight of people standing in water that shows how high sea level will get in their lifetimes in the place that they will live. And when you see that image, it really makes you realize what is happening. The good news about the Anthropocene, though, is that it proves that humans can control climate on Earth, right? Just been doing it in the wrong direction. So that should empower you to know that the changes that we make can have an impact, and those won't be immediate. It's going to take some time for those to flow through the system because of the timescales of these processes, but we can make change for the better. And so I hope that you leave this presentation tonight with that in mind.
Well, I think that was the last of our questions. Andrea, again, I can't thank you enough. We wish you were here with us in person, but
I do too.
I'm going to go out on a limb and say we would love to have you, if not next summer, in the near future, and share with you what's going on with the island, and you can share with us your latest research.
Absolutely, that would be wonderful. I'd love to see what's happening there. It sounds like you have a lot going on looking at sea level rise in the area. So
A lot of good things. Again, thank you so much for sharing your remarkable research and your work.
Thank you. And again, thanks to everyone for making time to be here tonight.
All right. Thank you. That was really great. Thank you.
I don't know if we stopped broadcasting. How do we do that?
I think we can. I think that's, yeah, you're controlling that. Again,
I don't know how to do that.
I think you just did, maybe.
Did I? I clicked something.
Something happened.
Okay. It says we're recording. I'm going to stop recording. Stop cloud recording. Is that okay, Lydia? Yeah. Okay.